this lecture by the fourth lecture, yes. The fourth lecture by Herman Verlinde, please.
Okay. Okay. I know it's been a long week and there's a lot of information that we've been processing. Today, again, I start sort of a new subject, and then I'll be connecting it with the number of things that I've been discussing earlier. So the topic for today is indeed this model that was introduced maybe 8 years ago by Kitaev as already an existing model, abbreviated by S. Sachdev, E. Kitaev, and it's just a quantum mechanics system. And it still has a bit of an interesting kind of role in the whole story, in my mind, because again, it's not a model that actually comes from string theory, but it captures sort of insights that came from thinking about what it underlies sort of from the principles that holography makes holography work, and it's a quantum many-body system. And it has sort of interesting, universal properties that apparently then capture precisely the kind of things that we've been talking about on the gravity side. So the SYK model, it's quantum mechanics, so indeed it will have a Hamiltonian. And actually, what's also interesting about it is that it's a type of model that you could even imagine building in a lab. And indeed, what it contains, so nowadays people indeed are quite interested in building things like quantum computers. So people talk about qubits, and a qubit is just a two-level system. And then indeed you can try to build sort of interactions between those two-level systems, and that becomes then a quantum many-body system. And the SYK model is actually of that type. Rather than actually introducing a qubit, what Kitaev did, he introduced what's called then Majorana oscillators. If you have a qubit, you can have operators that flip the spin of the qubit, which are like the raising and the lowering operators, and they're essentially Pauli matrices that act on a two-level system. And what the Majorana oscillators are, they're basically those Pauli operators, the raising and lowering operator of a qubit. If I have one qubit, I have both a raising and a lowering operator, so I'm going to have two Majorana oscillators for one qubit. So if I have n Majorana oscillators, I will have n over 2 qubits. We'll see in a second. So what are Majorana oscillators? They're basically defined through an anti-commutation relation. Let me call them psi. And then I'm labeling indeed psi I by index I going from 1 to n. And then the anti-commutation relation are basically those of gamma matrices, where the things anti-commute if I and j are different. And essentially, and maybe I should put a factor of 2 here, they square to 1 if they just if I and j are equal. This tells you that they square to 1. So this is the oscillator algebra. And indeed, it leads to a Hilbert space obtained by essentially starting, say, with some given state, and then you can start acting on the psi's on the state by acting with size. And these are called Majorana oscillators because many times if you have a raising and a lowering operator, you want to call one of them the dagger relative to the other. In this case, these guys are one and the same thing. So in some sense, the particle is equal to the antiparticle. The filled level and the non-filled level kind of are sort of at some level on equal footing. And this is why they're called Majorana oscillators. There's also a version of the SYK model where you would have sort of put a dagger here, but this turns out to be a slightly more convenient type of starting point. And then the claim is indeed that this leads to a Hilbert space whose dimension then is, as I mentioned, 2 to the power n over 2. So if n is large, this is a huge Hilbert space. And so now if you want to build something that would be an interesting quantum many-body system that has lots of sort of chance to be a quickly thermalizing system, and this was already an idea that sort of started building up after a paper by Praskil and Hayden, where they indeed sort of started emphasizing the fact that one should think about black holes as things that rather quickly start scrambling information. And then the idea is that if you have degrees of freedom that represent something that could potentially be a black hole, an interesting gravitational system, how do you make sure that the system quickly thermalizes? In most situations, and again, Jan was describing if you have a fluid or a gas and you try to scramble stuff when you throw it in there, in most cases the interactions take place locally, so you have nearest neighbors interactions. At some level, if you wish, you could try to imagine that these psis are living at certain locations in your mind, but actually these are just abstract labels. Nonetheless, let's think about them indeed as being sitting at certain locations. And then the way you want to have things sort of scramble very quickly is that you allow any fermion to interact actually with any other one, so that information can spread very quickly throughout the system. The Hamiltonian of the SYK model will indeed be of this particular type. And immediately I'm going to write down probably the more general version of the SYK model, where the order of the interaction, so the original SYK model had a quartic interaction, which already is interesting, but it turns out to be convenient to even be a little bit more general. And then there's a funny prefactor, P over 2. Let me indeed call it, do you know what I'll call this one? Parameter Q over 2. Yeah, let me call it Q over 2. Yeah, there are two notations for this parameter in the literature, one sometimes called P and sometimes called Q. Let me pick for Q for now. And then we're going to sum over I1 up to IQ. So Q labels the order of the interaction. I will have some coupling constant that indeed will have a label psi J1 up to J, labeled JQ, and then indeed I have my oscillators. Yeah, here I put the index on the lower end. It doesn't mean too much. Here I put them up. Maybe I should have inverted the notation here. You know what? Let me not worry too much about the summation convention. I'll just write it like that. That's okay. Good. So I'm summing over all the indices. These are random numbers. And here it tells me that I can pick Q arbitrary of these versions of these oscillators. I put them in the interaction, so it means that the information that might be encoded in one of these things after one time step can already start spreading out and influencing the state of all these other things. So this is sort of, sometimes it's called almost like an all-to-all interactions. Q, of course, we're still going to assume that it could be a big number, but it will not be as big as n. Later on, we're going to essentially take a large n limit, where the number of fermions is going to be certainly very large. And then if you do this systematically, it turns out that in this limit, the model that we're going to write down, quite surprisingly, this thing actually is soluble when n is large. Because it actually looks pretty complicated. Now, let's talk a little bit more about these numbers. So one aspect is indeed the all-to-all interactions. Another aspect is what we call disorder, where these things are random couplings. Now, if you have random numbers, of course, you don't want the numbers to sort of spread out over arbitrarily large values. So indeed, what you're going to do is you're going to typically pick a Gaussian distribution, and the Gaussian distribution then has a variance. And the idea is that all these numbers j indeed are Gaussian random numbers, each of them independently with some variance that is then labeled by a number that I maybe call curly j squared. And then if you normalize it, I think I have to divide it roughly by n to the power q minus 1. Just a normalization that covers for the large n scaling. So this is a Gaussian random variable. And as I mentioned briefly earlier, is that, okay, there are two ways of looking at this model. Indeed, one is to say, hey, I just picked this model, and each of these models is labeled by one particular choice of couplings j in this ensemble. Another thing that you could do is that this is called a disordered system. So there's disorder because of the fact that these couplings are random. And later what we're going to be doing is we'll indeed be averaging over all the elements of this ensemble. And this comes back a little bit to whether or not we should think about the underlying theory as just one single theory, or whether we should think about it as an ensemble of theories. In the approach that I'm going to describe, we're going to be averaging and we're treating the system as an ensemble of theories. Okay? Yeah, the mean is 0. That's right. Are there any questions about this? This is the definition of the SYK model. Why does one need to take an ensemble? Yeah, it is a good question. Of course, let's say it this way. One thing that is clear, that if I want to do computations in this system, which is our eventual goal, and certainly if you want to derive properties of the system, it's going to be very hard to do that while assuming that all these numbers are things that we have not specifically chosen. So then my theory will depend on the specific values of those numbers. And then I can write many papers by choosing many versions of those numbers. So if I want to derive universal properties, and this is often how physics still works, is that sometimes we're interested maybe in a specific system, but very often we want to derive universal properties of an ensemble of a more general class of systems. And then, of course, the convenience at this point is that this J is a given number. So J will be a parameter of the SYK model. Later on, I can introduce a temperature, and it turns out that then just a linear, certain combinations of the temperature and that coupling J, it will only depend on that combination. And then this parameter Q, that's another parameter of the model. So there are only basically two numbers that govern this model. Yeah.
We will get Swarzien quantum mechanics. So that one-dimensional safety is SYK model because this is also one-dimensional model, or it is different from the SYK model.
You mean if I take the large C limit of
Yes.
a safety?
Yes.
I can already maybe announce a little bit later what's going to happen with this model. Is that, again, this is a quantum mechanics model.
Yes.
So the holographic dual of this model is going to be indeed essentially a 2D gravity theory. One version of it is indeed JT gravity. It turns out that there's a slightly more general gravity theory because, again, as I mentioned, I have a few parameters in this whole game. There's another parameter that I could introduce, which is sometimes called lambda, which is q squared over n. It turns out that indeed we can take n to infinity, and then in some cases we can actually also take q to infinity, which turns out to be a useful limit.
Okay.
And then what's going to be useful actually is that there's what's called then also one of these double scaling limits, where we're sending q to infinity, and then still the n to infinity, but keeping this thing fixed.
Okay.
And in that case, you get a slightly more general theory, which is actually takes sort of the form of Liouville. It's called Liouville gravity. Which I'll write down a little bit later. But in both cases, the background, the classical solutions to this gravity theory will indeed have this equation that essentially that the curvature, the two-dimensional curvature, is negative.
Okay.
And then and this describes an ADS2 space-time, a two-dimensional anticyclic space-time. And two-dimensional anticyclic space again is this Poincare disk, and essentially the idea is that the SYK model, to some extent, is the theory that lives on the boundary of the Poincare disk, and the ADS2 gravity theory lives in the bulk.
Okay. So is there any analog of central charge in SYK model?
There is, meaning it turns out that this thing here indeed has a central charge.
Okay.
Has a finite central charge. Which is labeled in terms of that q squared over n parameter.
Okay.
If you take this central charge C to infinity, then this Liouville gravity reduces to JT gravity.
Okay.
And I'll explain that a little bit later, but I wanted to focus now on the quantum many-body aspects of it, and I'll come back to this later.
Okay. Thank you so much.
You mentioned a limit there in the lambda term. But in principle, you can choose these groups of Q elements to be any number of elements.
That's right. That's right. It has to be even, but that's it.
Okay.
It obviously has to be even because otherwise this Hamiltonian would be anti-commuting. If it's 2, then it's a slightly boring model because then it's kind of a Gaussian. It's a non-interacting theory. It's just quadratic. So the lowest value that's non-trivial is Q equals 4, and that's sort of the basic SYK model. But indeed, often nowadays, this double scaling limit is called the double scaled SYK if you do this thing. That actually gives you quite a bit of a handle on the theory. And it turns out that in this double scaling theory limit, the theory is very geometric. But today I'll describe a solution, a way of treating this theory that doesn't yet take this limit, but I'll explain how it simplifies things.
Thank you.
Yeah. A question up there still. Or maybe a comment.
So if we go back to the picture you drew yesterday, like that big diagram with the 4 corners, right?
Yeah.
I should think about this thing as sitting in the upper right corner, I guess.
That's right.
So is there any proposal or idea for what the left upper corner should be? What is the string theory kind of interpretation of this,
right.
this model? Is it some D-brain kind of?
Not really yet. There are elements, at least, that one can, of the SYK model that one can kind of uncover or embed in string theory, but there's not yet a way of embedding this particular model in a top-down construction. So as I mentioned, in that respect, this is actually sitting at a rather funny space point in sort of the theoretical development. Yeah. Because again, if we go back to how we started believing in holography, then really the D-branes in string theory played an enormously important role. So the D-branes have open strings attached to them. The things that are living on the boundary are basically usually the open string description. And holography is essentially what you might want to call an open closed string correspondence, and the closed strings living in the bulk. And it's very tempting to start thinking about these sizes, degrees of freedom that might be somewhere hidden in some kind of string theory. And I would say there's sort of pretty strong evidence that in the end this thing has to sort of land on its feet somewhere. Yeah. So actually a similar thing was actually happening earlier with the random matrix models, where indeed people were already representing low-dimensional string theories, indeed as this double-scaled matrix model. Intuitively, people later started suspecting that there might be a relationship with D-branes, but those models already had been written down before we had the D-brane interpretation. But later on, it turned out indeed that they could be interpreted as in terms of D-branes. So it's possible that the SYK model has a similar kind of place within string theory. Although, let me say the following. In the end, there's going to be a beautiful kind of universal theory coming out of this, which are these particular sort of low-dimensional gravity theories. It could well be that there are other quantum many-body systems that, when you take the large n limit, that you still land in this field.
Because it's only like the low energy thing which matches, I guess, right? So it's
currently it's the low energy. Although this you could think of as being the UV completion of those theories.
I think there's also, of course, this. If you look at the very late time behavior of this model, it's also pretty simple. It's sort of this chaotic theory localizes to some nonlinear sigma model. It's sort of an effective description of the chaos at late times.
Right. Now, another thing I should mention is the following, which has also led to a lot of interest later on, is that, again, that this whole notion of things simplifying when n gets large. Again, this goes back to the 70s, and then people already understood that you could have things that you call matrix models, which lead to these planar diagrams. And then you can have vector models, where your indices have just a vector index. That can also be solved in the large n limit, but the methods there look different. This thing can also be solved in the large n limit, but again, because essentially the Feynman diagrams are also going to be simplifying in this large n limit. But again, differently so this thing kind of sits in between the vector models and the matrix models.
Yeah, I see. Because the matrix size is in this case 2 to the power n minus 2, right? Is there as this extra exponential?
Yeah. No. Okay. So if indeed we want to relate this model to something that the triple S sort of random matrix model, then maybe this thing is the thing you should call L, and that's the size of the matrix that we might be interested in. Yeah. And then you start treating this thing, rather than giving it that specific form, you just treat this as if it's just some kind of random matrix. And it's not entirely surprising that eventually that this thing, maybe you don't even care that it actually looks like this. It just means this thing is just doing something random, and that's partly what's happening.
Can we think of SYK model as a living on some stack of D0 brain or some brain configuration of D0 brain, similar to some gauge theory construction of D brains?
No, at least as an intuition, I think it's not a bad intuition, but there's no explicit construction of that. Okay, so indeed, if this is a large n theory, then what's the method for solving it? One method for solving it is to just sort of work hard. Maybe, yeah. So in the end, one can summarize sort of a bit more the approach by identifying variables that indeed sort of make use of the fact that n is large, and in many cases, when you have a model with a large n, the things that start dominating is where indices are being contracted between different objects, because then if you sum, you have to often then sum over the indices, and that leads to a factor of n. So the things that start dominating are things where you sum over n. So it's natural to start thinking about something like, say, a two-point function, where I could take two locations, T1 and T2. Of course, let me still mention one thing. Now I have this Hamiltonian. I have these oscillators. Again, the oscillators are, say, in the Schrödinger picture, and then I can use the Hamiltonian to evolve things as the wave functions. Or I can take a Heisenberg picture, and I can make my psi's to be time-dependent. And then if I wouldn't have any interaction, basically this commutation relation turns then into an equal time commutation relation. And you could have a two-point function if you don't have an interaction. Basically, that two-point function would be like the propagator. So maybe before I discuss the two-point function, let me briefly write down the action that would lead to this particular commutation relation. So let me call it S0. Let me write it here. Of psi. It's the action. If I just take an integral over time, that's what actions should look like. I'm just doing this thing: sum over I, psi I, d tau, dt, psi I. This tells me indeed that the canonical conjugate variable to psi I is psi I, which sort of is what this equation tells me. Another small comment is that if psi I had just been an ordinary number, this would be a total derivative, but if it's anti-commuting, then this is a good first-order action. If you have an action like this, the propagator is simply the Green's function of the time derivative. And the Green's function of the time derivative is just the step function or a sine function. A sine function meaning it's -1 in one direction and +1 in the other direction. Maybe I'm not going to write that down. Homework exercise. Find the Green's function of this free action. But I'm going to here write down a 2-point function. So once I can think of the psi as a time-dependent object, I can put it somewhere at some location t or 1 and t2. And let me put a 1 over n in front of it. So this is the 2-point function, or it's not so much the 2-point function. It's just the bilocal operator of two fermions. Later on, indeed, of course, if we put it in the expectation value, we can take the expectation value of this thing, and I'll kind of use the two things interchangeably. I'll try to be clear at what point I'm going to take expectation values and when not. But this G is that object, and it turns out that it's going to be a bit easier to derive equations of motion in this interacting theory when we have this particular variable G. What we're going to do is we're going to essentially try to reformulate the whole theory in terms of that variable G. And the way to do that is essentially by starting indeed with the path integral. So I wrote down this action. Let me immediately sort of write down the more complete action. And let me, do you know what? Let me do that below here. So we've all seen this equation. I can probably still do it here. Why not? Let me use this blackboard then. So what is the action of the SYK model? That's the free action. And then, of course, we have to just subtract the Hamiltonian. So rather than repeating that Hamiltonian, let me just, do you know what? I'll abbreviate it a little bit. J times psi. Okay, fine. Again, there are all these indices, and there's the summation. Okay. And that's the summation over all these I indices, I1 up to IQ, whatever. Now, the first thing I'm going to be doing, indeed, I want to start deriving an action for this guy. And the reason why that's sort of a good approach, as I said, is that there's a summation over I here. So this thing is kind of a better what we would call a collective variable. So the thing that I'm going to be describing now is called dynamical field theory, or you can call it maybe a dynamical collective field theory. This is a single variable, G, and it captures the information of many variables. So it's a better average description. And indeed, what's going to happen in the next step is that what I'm going to do is, indeed, I'm going to do the disorder averaging over this variable J. Because this J is a Gaussian random variable, the psi's depend on time, J does not. So I just have to do a bunch of Gaussian integrals. They're not functional integrals, they're just Gaussian integrals. And when you do that, so you do the disorder averaging, you get a little bit of a funny looking action. And the reason is that since J does not depend on time, and there's an integral over time here that after I do the Gaussian integral, basically you complete the square in the way you're doing Gaussian integrals normally. You're going to get an action that actually will be bilocal in time. And I'll write it down for you. So after this order averaging, I claim that, oh, by the way, give me a second here. If I take two J's that are not, that don't have the same index, then they're statistically independent. I didn't write down this big delta function behind here, but basically if I would take two J's that have different indices, then their Gaussian average would be 0. So the J itself has 0 average, and if I multiply two J's that have different indices, it gives me. So that's what's good about that is that also that gives rise to actually a contraction of indices because there's actually a delta, Kronecker delta for each of these J labels. So I claim that this particular interaction here, after I do the this order averaging, actually turns into the following term. So there's going to be a coefficient J squared, the curly J squared, over this n to the p minus 1, n to the q minus 1. Integral d tau 1, d tau 2, I claim it what I'm going to get after I do my Gaussian integral over this J. I'm going to get a thing that looks like that. Because the indices indeed get contracted because the J with J again only gives the same, a non-zero answer if the indices are the same. This leads to that particular sum here. If I do it to the power q, indeed I get all these different terms. So this is psi to the power q. Here they're psi to the power 2q, but that's because I've completed the square of the Gaussian integral. And indeed I get a bilocal action because the J does not depend on time, and I basically square that integral. So this is what I'm get after Gaussian averaging. And let me double check the pre-coefficient. Are there questions about this particular step? Because again, this is, of course, also the motivation for introducing this variable g, because now you see that the action, this part of the action, now only depends on the on this particular variable, this two-point function g. I think I did that fine. Okay. Yeah.
So why do we have to square the integral?
Why do we have to square the integral?
Yes, in order to get the bilocal measure.
Yeah, so what's happening, and let me try to do it a little bit schematically. So instead of using all the indices, what I have, I'm doing an integral over a bunch of j's. I have a Gaussian integral where here there's a curly j squared. This is a Gaussian integral, a Gaussian with width curly j squared, and again I'm not writing down the factors of n. And then there's an integral over dt of this j times psi to the power q. Okay. This psi to the power q is just shorthand for this. Okay. Now this j doesn't depend on time. So I can write this thing as j times that thing. And now if I do this Gaussian integral, I have to complete the square. So I get this thing squared.
Okay, I see.
So that's why I get the double integral over dt.
Okay, thank you.
And that's, again, that's a slightly funny consequence of doing this order averaging. It's actually, to be honest, it's slightly related to the things that was mentioned earlier, that if you average over couplings, there was earlier discussion of the wormholes. Again, going back to Coleman in the 80s and others, people actually were sort of, so Coleman at some point started thinking about wormholes, and then actually a sort of a similar argument allowed him to argue that what wormholes actually mean is that the coupling constants in nature are random, and that we actually should be doing an ensemble over couplings constants in nature. And coupling constants in nature are the same throughout the universe. And if I start averaging over coupling constants that are the same throughout the universe, I'm creating correlations between here and somewhere very far away. In the ensemble average, things here and things there are going to be correlated because things over there are supposed to have the same coupling constant as here. Something similar is happening here. This j doesn't depend on t, but I'm averaging over it, which means that there are going to be correlations between different times, namely that they still have the same j. And those correlations are encoded in this bilocal action.
Okay. Thanks.
Are there other questions? I'm going to erase this because I want to write. So what you can see is that this g that I defined in this particular way appears in this term here. And maybe if I put the 1 over n in here, then this goes away, and then that's just the 1 over n, I think, in front of here. Actually, the n goes up. And I put the 1 over n inside of the power of q. There's I to the q? I'll take the fifth on this one. I'm not going to worry too much about. You can find the factors of I in this whole thing. I don't think it's going to be that instructive. The factors of n are actually more important. I put some arbitrary factors of n here, n to the q minus 1. And that n to the q minus 1 is a 1 over n to the power q, which sits here, times that n. And this is actually kind of important, meaning this 1 over n is just meaning I'm averaging this 2-point function over all the fermions. But this factor of n later will pay me dividend because it means that the action will have an overall factor of n in front of it. And that's precisely why large n limits often are useful, because if the action has a factor of n in front of it, then at large n I can treat the action semi-classically. And this is why the theory will be soluble at large n. Okay, so the next step is going to be the following, is that I'm going to essentially, I want to start integrating out the size in favor of the g. And the way I'm going to do that is I'm going to add another term to the action where I'm integrating, basically, where I'm introducing a Lagrange multiplier. So it's also going to be a bilocal action. I'm introducing a Lagrange multiplier that I call sigma. Sorry, I need to go all the way to the left to write that thing properly. bracket. Okay, so what have I done? I've introduced a Lagrange multiplier that imposes this particular equation. So these two things are now the same if I impose the equation of motion of sigma. Since basically this thing imposes a delta function, let me cheat a tiny little bit, but it's an okay procedure, where I decide that I'm going to just identify these two things, which means I can replace this interaction term, just this quantity, I can replace it by G. So I'm going to do that. Okay. So this thing here, after this order averaging, has been replaced by these terms here. So my full action now looks like this. So if you want, I can reproduce this this thing here by indeed integrating out sigma, imposing this delta function, using that delta function to replace this G again by that object, and I get the thing that I had before. Okay. So this is another version of the SYK model. And now, what's nice about this is that when I write it like this, this action has now become quadratic in terms of psi. All the interactions were here, but I've written them in terms of G. And the interaction now is just a quadratic, a Gaussian integral over psi. It's magic trickery. This was actually what the contribution of Sachdiev and Ye. Again, the model existed before their time, but this is how they, and of George and Parcolet, where they basically were able to kind of reformulate the SYK model in terms of something that's going to be called the G sigma theory, because G and sigma are going to be the variables of the two, of the new. Are there questions about this? Yes.
Like, oh, sorry. Integrating out the disorder averaging, get a nice form and have sum of psi to the power of k. Was the large limit important there? Or that was like independent of
no, this is this is independent of large N. It's also independent. Okay, that's actually a good question. Let me think about this.
I was thinking about the contractions that you could do. Anyway.
I would say the only sense in which the large N limit is important. One thing you could have asked, is it allowed that some of these indices are the same? I guess they cannot be the same because of. But now I don't think at this point I used large N, but there may be a more subtle thing that I have to sort of remind myself of. But at this point I think I have not used large N. Nonetheless, I was motivated by large N to sort of go to this variable. And as I mentioned, this N here will become very useful. Are there other questions? Yeah. Yeah. Sorry? What does it represent? Yeah, at least at the moment I still have psi, but I'm going to get rid of psi in a second after just integrating out psi. Let me still make one brief comment. So this thing is the two-point function. Give me a second. Maybe I cannot immediately. Oh yeah, here we go. It's actually interesting to look at the equation of motion of psi. The equation of motion of psi is that dt of psi plus, which is a function of t, plus the integral dt prime sigma t prime psi I, and maybe there's a 1 over n here, is equal to 0. So psi I satisfies, this is t prime here. So this is a function of t. Integrating over dt prime gives me a function of t. So this is, if you think about it carefully enough, the physical interpretation of sigma is that it's called the self-energy of psi. So it means that previously, if I didn't have the interaction, the equation of motion would simply have been dt of psi is equal to 0. But because of the interactions, I'm going to get sort of new stuff. And if you, so basically this encodes all the interactions that psi has with itself. So this thing is called the self-energy. So it does have a physical meaning. But in terms of the manipulations that I'm doing here, this sigma is simply the Lagrange multiplier that I'm introducing to impose this particular equation. So I'm going to write down indeed the collective mean field theory, it's called, or the dynamical mean field theory of the SYK model. It will look a little bit strange because what I'm going to do, I have this term sigma times g. I'll have that second term, so let me write down both terms. And I think what I'm allowed to do, by the way, I might be allowed to just put a factor of n here that gets rid of this factor of n. Because I want to indeed keep this factor of n out front of the action. That's just a rescaling of what I call sigma. So I have these terms. Those come from the second part of the Lagrangian. But then the psi piece, I can just integrate out. And since it's a Gaussian integral, when you do a Gaussian integral, in this case, there's no linear term in psi, so it's actually only the functional determinant. The functional determinant actually, when you do fermions, first of all, it sits in the numerator, not in the denominator if you do both, which it would be if you have bosons. Second of all, if you have Majorana fermions, you don't literally get the determinant, you get something that's called the Pfaffian. It's the square root of the determinant. So there's another term that looks a little bit funny. It's the log of the Pfaffian of the differential operator that I actually wrote down here. the thing that actually acts on the psi field of this particular differential operator. Yeah, let me write it d plus sigma. And what I mean by sigma is that it acts on psi in that particular way. So I have to write down a functional determinant, essentially, of this thing. So this is the dynamical mean field theory. It looks a little bit scary, but two things are going to be slightly simpler than the action. We can derive equations of motion from this action. And the other thing, it turns out that if we start taking this particular limit, it turns out that you can actually simplify this action quite a bit. The Pfaffian, if you square the Pfaffian, you get, basically, as I emphasized, if you write down the kinetic term of the, for example, the DDT is an antisymmetric matrix. It's because it's anti-Hermitian, at least at the partial integration. And indeed, if I do a Gaussian integral with fermionic variables, the only way in which the Gaussian factor can be non-zero is if the matrix that sits in between is antisymmetric. If I take the determinant of an antisymmetric matrix, it turns out that it's the square of something. It's automatically the square of something. And that thing is the Pfaffian. So the Pfaffian is the square root out of the determinant of an antisymmetric matrix. Yeah, but in some sense, this is kind of telling you a little bit more that you, specifically that you're dealing with something that's Majorana, that is real antisymmetric. But you're right. If for most practical purposes, you can think about it as half the determinant. Okay. So I'm trying to, maybe I'm being more fancy than I should be. And if I'm more precise, by the way, since the action comes with a minus sign and the Pfaffian sits in the numerator, there's a minus sign here. And sorry, yeah, and there should be a factor of n. Thank you, because I have n fermions, and I can declare now victory because I have my factor of n sitting out front. So that's the main gain of the whole procedure. We have gained two things. We've gotten rid of all these annoying I indices, so this is sort of a collective description. We no longer have any I indices. Indeed, the model only depends on this number Q and J, no longer on all these other variables. Plus, I have this factor of n sitting out front. Which tells me that I can treat this theory semi-classically. So if n goes to infinity, that's a classical limit. So at this point, yeah, you can. People actually have been putting this thing on Mathematica. At least you can start sort of trying to study this theory in many ways, just by looking at its equations of motion. So the equations of motion indeed become now important because of this last comment, is that basically the way to solve this theory is indeed to treat it classically, and you can try to look for saddle points of this theory, and they will play an important role in the story. So one equation of motion is simply to vary g. And if I vary g, I get the following equation of motion, that sigma is q. Maybe I could have put a factor of 1 over q here if I had been slightly more in my definition of j, but that's okay. Q times j squared times g to the power q minus 1. This is a bilocal function of tau 1 and t1 and tau 2 T1 and T2. This is a bilocal function of T1 and T2. So this is one equation. Another equation is varying with respect to sigma. And actually, basically what it tells me is that, let me define the following thing, notation. Sigma star G is the integral dt prime sigma t 1 t prime g t prime t2. It's called the convolution product. And indeed, this thing again is a function of t1 and t2. So this thing is a function of t1 and t2. Sorry, bracket here. Let this be differentiating with respect to t1. This g is a function of t1 and t2. And this is going to be a delta function. That's an equation of motion of this theory. One way of seeing it is that if I vary the Pfaffian, the log of this thing gives me 1 over this object. It gives me the inverse of this is equal to g. The fact that the inverse of this is equal to g, I can rewrite that equation by saying that g is the inverse of that, and this is basically the equation that the two things are each other's inverse. Okay. Are there questions about this? So these are the equations of motion. It's actually quite instructive to think about these equations diagrammatically. I might still do that, but for now let me maybe jump a little bit just in view of the time. Yeah, let me, do you know what, I'll still maybe say a few words about it, about the diagrammatics. That may be helpful. I just want to make sure I'm going to do this right. Okay. Give me a second. So let me think of G as something that looks like that. It's a two-point function. But I'm including all the possible interactions in the theory. Right? So what G is, it's the two-point function in the interacting theory. And therefore, I can take all the diagrams. Oh, give me a second. Right. The fact that sigma and G are each other's inverse means that I can think of sigma as being the inverse of this. So this equation give me a second. Let me still do the other thing first. Sorry about that. I want to, rather than going to the diagrammatics, I want to sort of make some other comments. Because I may want to do the diagrammatics in another limit. Notice this derivative with respect to time. I'm going to try to explain why Kitaev actually recognized that this theory has a soft mode. And that's maybe the place where I want to go. This equation essentially doesn't involve any scale. because it just relates sigma and g. This equation, if you go to very high energies, this time derivative will be important. If you go to much lower energies, only the second term will be important. Let me try to emphasize that a little bit more. So if I think about, and I'm going to again be very schematic, about this Lagrangian, and this is indeed an important comment. So the SYK action looks like this, and I should have maybe made this comment a little bit earlier. Let's put our renormalization group hat on. So what is our renormalization group hat? Is we're looking at a theory, and we want to determine which terms in the action are important at high energy and which terms are important at low energy. So what we're going to do is we're going to try to make this action scale invariant, and then we try to see if certain terms indeed resist being scale invariant, and then we try to see which of these terms dominates when we go to low energy. Okay. Now it turns out actually that what we can do is we can actually try to turn this theory into a conformal theory, where it actually becomes scale invariant. So let's try to make this theory scale invariant. Okay. Now there are two ways in which I could try to make it scale invariant, by first actually looking at each of these terms. But suppose indeed I insist that this will become scale invariant. The thing that stands out is when I look at this particular second term. Since I have an integral over dt, the total scale dimension of this thing should be 1 in order for this action to be scale invariant. Is that clear? Because I have one integral, I want this to be dimension 1. So suppose that psi has scale dimension 1 over q. Then this term indeed becomes scale invariant. This term then has scale dimension 1 plus 2 over q. Whereas this term has scale dimension 1. Now 1 plus 2 over q is bigger than 1, so this thing has a higher scale dimension than that. Which means that if this thing has a high scale dimension, it will become important in the UV, and it will become less important in the IR. So this is what we would call the UV term, and this is the IR term. Just for the sake of it, let's briefly take another philosophy where I say, hey, what if I would have chosen this thing to be scale invariant? If I would have chosen this thing to be scale invariant, this ddt has scale dimension 1. So psi has scale dimension 0. If psi has scale dimension 0, then psi to the q has scale dimension 0. And 0 is smaller than 1. And again, this term is the thing that dominates in the infrared. So that's basically the essence of the intuition that also Kitaev had, or I think this was understood at the time, is that this is, in the end, if you're looking at the infrared, it's as if you can drop this term and only keep that term. And the same is true for these equations, that if we want to find a regime where the theory is scale invariant, we can actually initially look for a regime where this term is subdominant. And then later on we can reintroduce this term when we are interested in what happens in the UV. So then, indeed, we're going to get equations that only involve the sigmas and no longer involve the t. Okay. Okay.
I was wondering, should we worry about any anomalous dimension this operator may get? Because it seems that it might be relevant in large Q limit, at least.
Yeah, good question. This is a naive argument. So this is how you start RG. Always when you look at the Lagrangian, you try to figure out which terms are important in the infrared and which ones are important in the UV based on just scaling arguments. I was using here scaling arguments. And I use those scaling arguments, and often in practice, if you use the scaling argument to determine which term dominates over the other, you often indeed get the right answer for which term dominates. If you want to get the actual scaling dimensions, you have to start working. So indeed, you take this theory, and then indeed you start making a scaling ansatz, if you wish. And indeed, what is the scaling ansatz? The scaling ansatz would be that this thing indeed will have a certain scale dimension, that G will have a scale dimension. And then indeed, I'm not going to necessarily assume that it will go like 1 over Q. It turns out that it will go like 1 over Q if I don't do a double scaling limit, if I take Q large, etc. But nonetheless, if I want to look for a scaling ansatz, so there's a conformal regime where G, tau 1, tau 2, it will look like the Green's function of the free theory, but then indeed I'm going to have T1 minus T2 to the power some delta. And then later I can try to find a self-consistent equation that will determine this delta. So this is an ansatz that I can do. And then sigma T1 T2 simply because of the fact that sigma times G also should be scale invariant, then we'll have a similar form sine T1 minus T2. T1 minus T2 to the power 2 minus delta. This 2 is there because this is now a two-dimensional integral. This should have dimension 2. So this is going to be an ansatz, a scaling ansatz if you wish. You plug these equations into these equations, and you're going to get equations for delta. I'm not going to do that. It's actually an interesting exercise. You can find it in the literature of how to do that. And it turns out that you can find a self-consistent solution for delta. Are there questions about this? Now, at this point, I'm going to reintroduce the theme that I had before, namely, this looks scale invariant. When I was earlier talking about two-dimensional CFTs, we had conformal invariants that allowed us to do reparameterizations of the coordinates z. So let's look if we can do reparameterizations of the time variable t. This action, I've now dropped basically also this dt term. So if I dropped it in the equation there, then basically I'm dropping it here as well. If you think about it carefully enough, this action itself will also be then will actually have a reparameterization symmetry. So if I do reparameterizations, it turns out that the equations of motion will remain. Except that I have to do the reparameterizations in such a way that these things transform according to their scale dimension. So the SYK model, and again, this was the observation of Kitaev. Has a soft mode. And it's basically a reparameterization mode. Where the variable t is going to be reparameterized to some other variable, which I call tau of t. So if I go to a new coordinate system, then if indeed give me a second. I think it's delta over 2. Yeah, so if you do this coordinate transformation, then G transforms as a form with scale dimension delta over 2 in the 2 arguments. That's compatible with this particular ansatz. And then if sigma transforms analogously with this scale dimension, you can verify that these equations actually are invariant under doing that reparameterization. For example, again, this thing will transform the right way, and everything kind of the equations will stay. So indeed, this conformal regime has indeed a soft mode that allows for these degrees of freedom essentially to go unimpeded, at least according to those equations. Are there questions about this? This is something that it's useful to verify. I don't think I want to work it out on the blackboard, but the claim is that that mode is there. And this is sort of an example of something where you can start thinking about essentially a Goldstone mode. So there is this symmetry, and now this is only a symmetry of the theory where I actually had dropped the DDT term. Keeping the DDT term was actually, of course, we'll reintroduce this term. And then the basic claim is that when you reintroduce the DDT term, you're going to derive a non-trivial action for this tau. Because the fact that it's a symmetry means that if I drop this term, then this action is actually doesn't depend on this degree of freedom tau of t. If I reintroduce that term, I will find an action for this tau of t. Okay. Yes. Sorry. What I'm saying is that this is an arbitrary degree of freedom. So it's called a soft mode. And basically what it means is the following, is that when I'm integrating over G and sigma, I can do that integral in 2 steps. I can fix g and sigma initially, and then rather than integrating over g and sigma, let's integrate over all g and sigmas that are related in this way. Meaning I'm parameterizing the g and the sigma by this variable tau. Oh, sorry, this tau should, yeah, it's tau of t1 and tau of t2. So I have this variable tau, and I'm using that as my first integral. And then I'm going to find that the action doesn't depend on that tau. So then I have to ask, okay, well, hey, because I was dropping a term, let's try to find out what actually the dependence is on this degree of freedom. So it's actually, I would say it's a rather subtle argument, because basically what has happened now is the following, is that I went from the theory, the UV theory. So SYK has many scales in it. There's a scale that's dominated by in the UV, that's dominated by this term. So in the UV, this term is kind of weak compared to that term. So I have Majorana fermions, and I can see them as interacting once in a while with each other. Then I go to the conformal regime. So I go farther down, I get interactions, and eventually there's going to be a conformal regime where this ansatz is pretty good. But then strangely, in that conformal regime, there's actually a soft mode. And soft modes actually are also infrared modes. And so in the conformal regime, there's this soft mode, and that soft mode will get an action. But the action is going to be defined by means of the UV term that I dropped. So the fact that I was dropping the UV term was actually a small mistake. And I can correct the mistake by reintroducing it and then trying to figure out how it depends on this tau degree of freedom. Yeah.
What characterizes the conformal regime? Are we just here saying that whenever these ansatz are good? That's what
It's a good question. So indeed, whenever the fact that the ansatz works, so if you plug this in here, you're going to find solutions. Mm-hmm. And in particular, yeah, right. So yeah, you're going to find that it works. Now, physically speaking, indeed, we know that we were at a lower energy scale. I would say once we have determined the scale dimension delta, and I could have written down a formula that one gets for arbitrary Q and J of how it depends on the equations. But the way you're going to figure out that when this term is going to be important is to just figure out when this term again becomes non-negligible compared to those.
But comparing those two is just comparing the energy scale we want to do the
right.
physics.
So I can indeed always find an energy scale where the second one dominates over the first one.
But my question was about what is this conformal regime just the IR regime we are talking about? Or
yeah. So by the way, one thing that I didn't do in the discussion here is that when we talk about regime, what do we mean? We can put this system at finite temperature if you wish. Mm-hmm. And then the temperature will determine at what energy scale we're probing the theory. Mm-hmm. So when I say there's a conformal regime, it means that if I go to lower temperature, then eventually I might end up in this regime. But then if I go back to higher temperature, I may need to worry about that extra term.
Okay. Thanks.
But I should say, an important point is the following, is that this conformal regime actually only makes sense. Previously I was saying, hey, I could integrate over tau of t, but then the action doesn't depend on it. So what I should do is I should treat this tau of t as what we call a collective mode, in the following sense that I shouldn't initially integrate over it. I should fix my coordinate system for initially, and then only after I've introduced the action for this degree of freedom, then I can start integrating over it. So let me introduce that action. So here's the thing that another trick that one can do. So I told you that this particular term is the thing that breaks the scale invariance. Now, what's actually interesting is what I could do is I could call this whole combination here, I could call that sigma hat. This is not sigma hat, this whole combination is sigma hat. So but if I put a hat here, I've made a mistake. I've included another, I should subtract the DDT from that sigma hat in order to turn it into sigma. So rather than keeping that term here, which I can drop, I could have added another term, or maybe subtracted it, where I do the following. I do integral dt dt, and I take the d2 derivative of g t1 t2, and I actually take the limit. Sorry, there's only one integral. I claim that if I shift the ddt in this thing, since there's a double integral here, this dt actually has a delta function of t1 minus t2 in it. And this additional term is just a way of representing the kinetic term of the fermions, but now in terms of this variable g. So it's an integral over t1. Temporarily I have the t2 in here, but I'm taking the limit where t2 goes to t1, and that's the kinetic term that I'm adding. And if I do that, then indeed I can just replace this thing by sigma hat. So this action is equivalent to the one I had before, and then this first, these terms are all scale invariant and reparameterization invariant. And this is the term that breaks the reparameterization symmetry. Okay?
If you plug this back here, this GE, you're going to get 1 over time difference square. And if you take this reparametrization mode, the new factor of 2 almost cancel, but it seems you're going to get a Schwarzian difference in general.
If you reparameterize them. You're jumping ahead. Yeah. It's true. So these, if I do this reparameterization at non-incident points, and I do this thing nicely, the reparameterization symmetry is there. Okay. The Schwarzian shows up once I take this ansatz. I do the reparameterization, and I take the limit where the points come close to each other. So again, one of the homework exercises, we're doing something similar, is that if I take a 2-point function that has some scaling behavior like that, I reparameterize it, and I take the limit where the 2-point function goes to two things sitting on top of each other. Then I can get something that looks like a Schwarzian. So indeed, this object here indeed is not reparameterization invariant. For the same reason as that the stress tensor that we were talking about earlier is not reparameterization invariant. So that's the derivation, is that you do the reparameterization. You take this ansatz, you plug it in here, and you take the limit. And you're going to get an object that will only depend on that reparameterization mode. And the claim, and there are quite a few subtleties in this derivation, I should say. There are some special limits where the following claim is sort of more under control. But basically, that this particular thing that I'm writing down here, where indeed I take the d t2 of g t1 t2, again limit t2 to t. This will become the integral dt of the Schwarzian of tau of t of t. And this is how the Schwarzian action comes about. Again, Kitaev, his argument, I think, was really based on the fact that if he looked more carefully at the kinetic term, that there are these transformations, again, A tau plus B, where tau itself goes to A tau plus B divided by C tau plus D. This is a symmetry that one could consider on this variable tau. And this symmetry is unbroken. The symmetry that is broken is the symmetry where, indeed, I reparameterize time. So tau as a variable, indeed, is what we call a pseudo Goldstone boson. The reason why it is a pseudo Goldstone boson is because there's actually a term in the action that doesn't respect the symmetry. So whereas we seem to have had initially a symmetry, if you look more carefully, there is a term that explicitly breaks the symmetry. That's what we call a pseudo Goldstone boson. But this symmetry remains unbroken, and this for him was already an intuition of why this had to be the Schwarzschild. But then indeed there's sort of a back of the envelope, I would say, derivation along those lines. Okay, so this is about as much as I can say about how I can go from the SYK model to the Schwarzschild. In view of the time, I think. I should stop.
So how come we see the double scaling limit in the theory?
How do we, sorry, to see the...
If you want to take the double scaling limit that you talked about before, how do I implement it on this level?
Yeah, let me mention that briefly. What happens then is that in the double scaling limit, Q becomes large, and the scale dimension of psi becomes very close to 0. It also means that actually this delta becomes very small. And if this delta becomes very small, then I can approximate G by this sine function plus a small perturbation. And I can call that small perturbation, I can call it phi, say, okay? Sigma is a very high power of G. And if I have a thing that looks like 1, which is basically the sine function plus a small number, and I take it to a very high power, if the small number is of order 1 over Q, and I take it to the power Q, I get an exponential. So this, so basically what I'm going to get a field phi that labels the deviation of G from the free 2-point function. I'm going to get an interaction term that's e to the phi. And it turns out that if you actually take this action and you integrate out sigma, then your phi will just get a standard kinetic term. It will be the kinetic term d tau 1 of phi times d tau 2 of phi, dt2 of phi. It looks like a free scalar field, but it propagates in this t1, t2 space. And it will have an exponential interaction. So this G sigma theory actually reduces to something that is actually this Liouville gravity theory. So indeed, in the double scaling limit, you can go from this theory to Liouville gravity. Indeed, with finite central charge. No, in this limit, I would say n goes to infinity. Still, n and q have still been both sent to infinity. So the Hilbert space is infinite.
So, is it known any a stringy uplift of any of those theories, JT gravity or Liouville gravity?
Liouville gravity plays a role on the world sheet of strings. In in AGT type systems, Liouville theory plays all kinds of roles. There are certainly corners of string theory where Liouville theory kind of is popping up, but I wouldn't say that there's a particular decoupling limit of string theory where literally this thing would be in the landscape of possible string theories.
Because
but for Liouville gravity, you could still have some hope. JT gravity is sort of still a limit, actually, of this thing. But I would say currently we don't, and this question was indeed asked earlier, we don't have a sort of a top-down way of deriving these theories.
More questions? Well, it's not. If not, let's thank Herman again. All right, let's reconvene here at 11:30.